about the type of failure, specifically fatigue failure, and how to obtain the SN curve. So this curve will be benefit us in the design process so that we can predict or estimate the life cycle of the component that we develop. So let's have a review here together.
Excuse me, sir.
I think you didn't hear the sound, right?
Yes, sir. We hear the
Okay,
sound
please
of
wait a minute. Please wait a minute. Okay, let's restart again.
Fatigue failure, and it accounts for the vast majority of mechanical stresses well below the material's ultimate strength. Components which are subjected to loading which varies with time can fail at stresses well below the material's ultimate strength. This is known as fatigue failure, and it accounts for the vast majority of mechanical engineering failures worldwide. The bolts in an office chair, the crank arm on your bicycle, and pressurized oil pipelines are just a few examples of components which are subjected to time-varying loads and may be at risk of fatigue failure. Fatigue failure occurs due to the formation and propagation of cracks. It is a three-stage process. The first stage is crack formation. This usually occurs at free surfaces and at stress concentrations. In stage 2, the crack grows in size. And in stage 3, after the crack has grown to a critical size, fracture occurs. So how can we figure out whether a component is likely to fail due to fatigue? One common approach is to run fatigue tests by subjecting a component or test piece to a large number of constant amplitude stress cycles and counting the number of cycles until it fractures. If we repeat this test a large number of times with different applied stress ranges, we can plot the results on a graph, with the number of cycles to failure n on the horizontal axis and the applied stress range s on the vertical axis. Because the number of cycles to failure can be very large, a log scale is usually used for the horizontal axis. By fitting a curve to the data points, we obtain what is known as an SN curve. The SN curve allows you to calculate the number of cycles until a component is likely to fail for a given stress range. For example, if we have a stress range of 100 MPa or 15 KSI, this SN curve tells us that the number of cycles to failure is 500,000. If we know that our component is subjected to 1 cycle per minute, we could predict that our component will fail due to fatigue after approximately 1 year. Fortunately, we don't have to perform these time-consuming fatigue tests ourselves. SN curves for many different materials are already published in different engineering codes. For some materials, and in particular for ferrous materials, it is important to note that the SN curve at a very large number of cycles becomes a horizontal line. This is known as the endurance limit. Theoretically, the component could be cycled at stress ranges below this level forever, and it will never fail due to fatigue. This makes the endurance limit an important fatigue design parameter. It is common to differentiate between high cycle and low cycle fatigue. High cycle fatigue occurs when the applied cyclical stresses are low, and failure occurs after a very large number of cycles, typically more than 10,000 cycles. Because the stresses are low, we are only dealing with elastic deformation. Low cycle fatigue involves higher applied cyclical stresses, and failure occurs after fewer cycles. Because the stresses involved are above the material's yield stress, both elastic and plastic deformation occur. In these cases, a strain-based approach, using, for example, the Coffin-Manson relation, is usually preferred to the SN curve approach. If we return to the data from our fatigue tests, we can see that there is a large amount of variability in the data. This is typical for fatigue tests, even when identical test pieces are used. If we use a best fit SN curve, as we have done here, there is a significant possibility that our component will fail at a much smaller number of cycles than the curve predicts. This test piece, for example, failed at a much lower number of cycles than predicted by our SN curve. For this reason, SN curves published in engineering codes are normally shifted downwards by a certain number of standard deviations to give a reduced probability of failure. Here, by shifting the mean curve down on the vertical axis by 2 standard deviations, we have reduced the probability of failure from 50 to 1%. Fatigue tests are usually run for the constant amplitude fully reversing cycles you can see here. The same stress magnitude is applied in tension and in compression. Let's define a few terms. The stress range is defined as the difference between the maximum and minimum stresses. The stress amplitude is defined as half of the stress range. The mean stress is the average of the maximum and minimum stresses. In this case, the mean stress is 0. But this is only one very specific type of loading. In some cases, we might have a mean stress which is not equal to 0, as shown here. This mean stress will have an effect on the fatigue life. A tensile mean stress will typically result in a shorter fatigue life. One way to account for a tensile mean stress is to use SN curves derived for specific values of mean stress. But these are often not available, or would be time-consuming to obtain. Another approach is to use the Goodman diagram, which adjusts the endurance limit to account for a mean stress. Let's see how it works. On a Goodman diagram, the mean stress is shown on the horizontal axis, and the stress amplitude is shown on the vertical axis. A straight line is drawn between the endurance limit, at a mean stress of 0, and the material ultimate tensile strength, at a stress amplitude of 0. If our cyclic loading conditions are located below the Goodman line, our component will be safe from fatigue failure. There are a few different variations of this diagram, as you can see here. This approach can only be used to determine whether a component will have an infinite life. It doesn't allow us to calculate a fatigue life. In many real-world cases, the applied loading is likely to be far more complex than what we have considered so far. We can use techniques like the rainflow counting method to simplify a complex stress spectrum into a number of simpler, constant amplitude cycles. Miner's rule allows us to account for the cumulative damage caused by each of these different constant amplitude stress ranges. It calculates the damage fraction D as the sum of the fatigue damage contributions for each stress range. The individual contributions are calculated by dividing the number of cycles by the number of cycles to failure for that stress range. The damage contributions from all stress ranges are then summed. If the total sum damage fraction is greater than 1, fatigue failure is considered to have occurred. In this example, the damage fraction D sums to 0.94. This is less than 1, and so fatigue failure has not occurred. If the structure we are assessing contains an existing crack, the SN approach is not suitable for determining the fatigue life. If the dimensions of the crack are known, we can instead determine the fatigue life using a linear elastic fracture mechanics approach. This involves calculating a critical crack size, which would result in fracture, and using a crack growth law to calculate the time required for the crack to grow to this critical size. But that's enough about fatigue for now. Stay tuned for more engineering videos.
Okay, that's our first video, which gives us a brief review about what is fatigue failure and uh, the method that we use to analyze that kind of failure. Okay, so what do you think about this fatigue failure? Do you have any comment or question about this video?
Sir, excuse me. I want to ask you something.
Yes, please, Sultan.
Okay, first I want to ask about Miner's law. So there is a small n that refers to the number of cycles, and the capital N to refer the number of cycle to failure. And there are we have different amplitudes. So which amplitude will have SN diagram each other, sir? Or we only use one SN diagram? Or every amplitude will have their own SN diagram? I just want asking about that, sir.
Okay, I understand what you ask about, but we will postpone the discussion for your question. Let's ask other friends about this video. Okay, so any other than Sultan have question about this fatigue failure, fatigue diagram? Okay, we have first question for Sultan. Let's save it for a while. I want to know how about the other response. We have more than 30 students here. Okay, so all of you already understand about this video?
Not really, sir.
Not really. Okay, so what you don't understand from this video? What is your question?
I rather confused, sir, with Miner's rule, sir, actually.
Okay, same question with Sultan?
Yeah, I have question. I rather confused if there is a prototype, maybe like. Yeah.
Okay, so the example in practice, is that right?
Yeah. If I have like, what is if we made some tower like things like this for carry the weight from the bottom to top. I don't know what is the name, but if miners apa ya?
Okay, let me help you. So first, you are confusing about what kind of real example to apply this uh, equation. Is that right?
No, sir. If we
No?
have like some contractor, what is like
Mm-hmm.
this,
Mm-hmm.
bring the load from bottom to top. Uh, we know that stress in this will be different, sir.
Yes, of
So
course.
yeah, we use minors rule. We use minors rule. So we use minus rule for different parts, sir, or for just one thing that we uh, calculate together.
Okay, I understand. So for for Edgar question, we come back to the very early discussion that all the design of the machine elements must be must be calculated at the most critical point. So that's the first concept. Any calculation, any analysis that we made must be conducted on the most critical point. So if you have this kind of beam, is and this beam support some load here, and this load, for example, pump, compressor, or something rotating machine hold in here. Then during the operation, it will vibrate. Okay, so this beam will move up and down periodically, depend on the frequency of this machine. Okay, so it will give the displacement on the beam. And when the beam displaced like this, it will create or generate stress. And the maximum stress will be on the surface of the beam. Please remember that the normal distribution on the beam due to the bending will be 0 in the middle axis, in the centroid, and will increase to the maximum on the surface. Okay, but which surface? We have surface along this beam. So of course, it will be maximum near the supported point. So it will be here. So this point will be our critical point. So we will conduct our analysis on this point. So in previous discussion, we usually think that this sigma or the working stress here created by bending is only static. Now, because we have fluctuating load here created by the vibration, then this bending stress also fluctuating here. Okay. So this is our critical point. So we have to conduct our analysis here, not on the other point. Because if during design, if we keep this point safe, then all of the structure already safe. We can guarantee that all other point on the beam will be safe from the failure. That's the first answer. Okay, so relating to the minor rules, For example, here, in our example, this machine, this rotating machine, creates only a single periodic signal, only single vibration like this, very simply. So it contains only single amplitude and also with single frequency. But in actual condition, we have many kind of machines that put in here. We have motor, we have compressor, we have pump, and any other machine that create vibration. So the response will be complicated then. As given in the video, maybe looks like this. So how we can decompose this complex signal into this individual signal. So actually, if we have several signal with different amplitude and with different frequency like this has A1 amplitude and the frequency omega 1, and this is A2 omega 2 and so on. If we combine this, then the signal will be looks like this. Or in other words, we can decompose this complex signal into this individual signal. So if we are able to do this, then we can analyze, we can doing analysis the fatigue failure for each signals. Okay. So here we have several vibration signal or several fluctuating load. So how to apply the minor rules on this type of signal, on this type of load? So first, if we have the information about this beam material, so this material only related with a single SN curve. Okay, so one SN curve for one material because it is the properties of the materials. Okay, one material can only has single SN curve. So even if we have several fluctuating loads apply at the same time, we can evaluate the fatigue failure using only this single curve. How do we do that? So that's why minor rules explain his method. Okay. So first, we have to know how to evaluate the cycles, the failure cycles for this each load. Okay, so for example here, because it has larger amplitude, okay, for example, it related with the sigma 1 and sigma 1 is here, then it will has the life cycle of N1. And for this second stress, second cyclic load, it relates with sigma 2, and because it is lower than we have here, we have N2 for the sigma 2. Then minor rules describe that the failure will happen if T is equal to or larger than 1. And what is T? T is the accumulation of damage created by each load. So this single load contributes to this failure, and this is also contribute to the failure, and it will be accumulated. So that's why it's sum here. So here we have for each load, we make the ratio between the cyclic life for this each load uh, with the ratio of uh, the total or uh, the overall damage here. So that's why when this sigma 1 create, for example, about 50% of the damage, and this sigma 2 20% of the damage, then it will be the D is less than 1. So it will save from the fatigue failure. Means that this load, this combined load will not induce any damage, will not induce fatigue damage on the structure. So is that answer can help you?
Sir, I want to ask you more, sir. If we saw like beam, sir, applied beam, how many some stress range we approve, sir?
What do you mean?
You say there is like theta sigma 1, sigma 2, sir. How many sigma how did we know how much sigma we use, sir?
Oh, okay. So in vibration, mechanical vibration, you learn about how to decompose the vibration signal. Okay, so you can use Fourier transform, or you can use wavelet analysis. Okay, so for this method, you change or you transform this very complicated signal in time history. So this, for example, stress into frequency base. So how to do that? So for example, for this signal, you have this kind of amplitude with frequency. So here you will have, this is the amplitude and this is the frequency. Okay, so this is omega 1 and this is sigma 1. It will be shown as bar diagram here. And for the next component, you will have larger frequency here, but smaller amplitude here. And actually, it contains many amplitude and many frequencies for this single vibration response. So to obtain this kind of diagram, we can use Excel, but you have to activate the data analysis for Excel, or we can use MATLAB to obtain this kind of diagram, to convert this. So Using this diagram, we know at this omega, what is the amplitude, and in other frequency, what kind of amplitude we have for this single measurement. That's how we do the signal decomposition, Edgar.
Okay, sir. Thank
You're
you very
welcome.
much.
Okay, how about Sultan? Is that answer can help you?
Oh yes, sir. It's really helped me. Thank you very much.
Okay, you're welcome. Any other
Uh,
question?
can I ask you something more, sir?
Yes, for sure, Sultan.
Okay, I want to ask about how do we know about the small n? How do we know about the total cycle every in each amplitude? So we will have the different amplitude tracer when we have the
Yes, different
fluctuating load.
amplitude and different frequency.
Nah, so based on that, I just wondering to know about the total cycles in each amplitude because I just wondering the small n is will be different each other or will be similar because they are just acting in the same material. So when we have a beam, the load those load will just acting to the that beam, sir. So I just wondering about that.
Okay, so let's see what Miller's rule define. Okay, let's take a look back here. Sorry.
The mean stress is the average of the maximum and minimum stresses. In this case, the mean stress is 0. But this is only one very specific type of loading. In some cases, we might have a mean stress which is not equal to 0, as shown here. This mean stress will have an effect on the fatigue life. A tensile mean stress will typically result in a shorter fatigue life. One way to account for a tensile mean stress is to use SN curves derived for specific values of mean stress. But these are often not available or would be time-consuming to obtain. Another approach is to use the Goodman diagram, which adjusts the endurance limit to account for a mean stress. Let's see how it works. On a Goodman diagram, the mean stress is shown on the horizontal axis, and the stress amplitude is shown on the vertical axis. A straight line is drawn between the endurance limit, at a mean stress of 0, and the material ultimate tensile strength, at a stress amplitude of 0. If our cyclic loading conditions are located below the Goodman line, our component will be safe from fatigue failure. There are a few different variations of this diagram, as you can see here. This approach can only be used to determine whether a component will have an infinite life. It doesn't allow us to calculate a fatigue life. In many real-world cases, the applied loading is likely to be far more complex than what we have considered so far. We can use techniques like the rainflow counting method to simplify a complex stress spectrum into a number of simpler, constant amplitude cycles. Miner's rule allows us to account for the cumulative damage caused by each of these different constant amplitude stress ranges. It calculates the damage fraction D as the sum of the fatigue damage contributions for each stress range. The individual contributions are calculated by dividing the number of cycles by the number of cycles to failure for that stress range. The damage contributions from all stress ranges are then summed. If the total sum damage fraction is greater than 1, fatigue failure is considered to have occurred. The damage contributions from all stress ranges are then summed.
Okay, let's stop here. Okay, so the question is how to know the cycle of each amplitude. Is that right, Sultan?
Yes, sir.
Okay, so the number of cycle for stress range for let me write here. Okay, so the question is how to know the number of cycle for each component of the signal. Okay, if we apply okay, if we okay, for example, at a given time for analysis, here we can obtain the cycle number of each signal based on their frequency. If we know the frequency, we can calculate the cycle number for a range time of analysis. So that means if we have larger frequency here, we will have larger cycles number for this signal. So that's how we obtain the number of cycle for a given range time of analysis. But this number of cycle is not related with this. This number of cycle means that this is the fatigue strength. Okay, so for a given SN curve, so this is S and this is N. So for example, here we have large amplitude here. So here we have sigma 1 here, and here we have number of cycles to failure, okay, and 1. So the question is, how about the number of cycle for stress range? Okay, so in the analysis for Miner's rule, we have to estimate. Okay, we have to estimate usually for the design if the cycle number is larger than 1 million or 10 million cycles. If the cycles is larger than this, we call this has infinite life. So here we have to describe the sorry, that's not how I should explain. Okay, let's have a point of view like this. If we have the product here, so if we have the product we have to design this product for a finite life or infinite life. Okay, so for infinite life, we have to make sure that uh, each each cycle will have uh, will be located below this fatigue limit for each component. For each component, so for we have to make sure that the maximum amplitude will not uh, will not appear above this fatigue limit. Okay, but for finite life, uh, we have to design how many cycles that this product can resist. So, for example, for 1,000, 100,000 of cycles. Okay, so for this cycle, we can estimate how how long the operating time for this machine. So, for example, if it has 100 omega, then we can estimate for this cycle we can operate this product how long, how many seconds. Okay, so this is the estimate life, and we can apply these cycles to this number of cycles for this stress range. And if we have another amplitude with different omega, then we can have another number of cycle for this stress range. Okay, so because we have two different load here, we can uh, we can add or accumulate the contribution for each load here. Okay, maybe this explanation is still not clear, but the patient maybe for the next video or after we have several example, we can make it clearer. Okay, so please postpone about this discussion. It's better to give you the example then. Okay, so uh, for now, let's take a look about the SN curve. Before Miner's rule, we have to understand about the SN curve itself and how to apply it to solve the fatigue failure in the component with a single signal, only with single type of loading. Okay, so Sultan, we will postpone this discussion. Is it okay for you?
It's okay, sir.
Okay, good. Okay, let's move to the next video.
Excuse me, sir. I'm sorry, sir. Can I ask a question?
Yes, for course, Bella. Please.
In the video, what is the difference between Goodman, Soderbergh, and Gerber, sir? And
Okay.
what condition we use each of them?
That's good question. So for that, we have to see the next this following video. Okay, please have a moment to watch this video.
Fatigue test. Many everyday items are not loaded uniformly, but rather non-uniformly with periodically changing loads. This is quite obvious frames, handlebars, and the term fatigue is used because it takes some time for the failure to occur under repeated loads. The problem with materials is that they normally endure less at repeated loading than with a once-only load. The wire does not break when first bent, but bending it back and forth repeatedly leads to an early fracture. This bicycle crank arm had only been able to endure the cyclic loading for a certain time before it broke. The fate of the garage door spring was the same. It had borne the opening and closing of the garage door about 60,000 times before it finally fractured. The broken exercise equipment, a torn blade of a fan, due to cyclic, often repeated loading. How can we make sure that frequently used steel in our laboratory? Hot-rolled steel rods made from the structural steel S235JR are used as base material. In order to eliminate the influence of the surface and to stress the material in a well-defined manner, suitable specimens have to be machined from the rods. This specimen type would be ideal. The shoulder-shaped ends have been designed for safe gripping. The actually tested region is cylindrical with a diameter of 6 mm. The material tester goes to the workshop to get 10 specimens manufactured from the rods, not just one. All of the specimens are as identical as possible. Back in the lab, he has all specimens ready for use and picks out the first one. He mounts the specimen carefully and securely into the fatigue testing machine. Together with 2 half shells, he inserts one end of the specimen into the right specimen grip. With a union nut, he locks the right end of the specimen. Likewise, he mounts the left end of the specimen into the left specimen grip and tightens the nuts. The preparation is now complete. The material tester then selects the appropriate test parameters on the control computer. He intends to load the first specimen alternately with a tensile force of 7 kilonewtons and a compressive force of 7 kilonewtons. The mean force is 0. A click on the start button and the testing machine begins to stress the specimen periodically. Our fatigue testing machine is equipped with a mechanical resonance drive. The specimen is connected at its left grip via a load cell to the machine frame. At the right grip, a spring is mounted, and there in turn a mass. An imbalance stimulates the mass to vibrate. Longitudinal guides prevent the mass from vibrating in the transverse direction. Via the spring, the test force acts on the specimen. By varying the excitation frequency of the imbalance, the test force can be controlled. In our case, the specimen is loaded with about 25 cycles per second. Meanwhile, the first specimen has already endured over 300,000 load cycles and still seems to be intact. In reality, however, several cracks have already developed starting from the surface, the so-called fatigue cracks. With each load cycle, they grow a bit further into the specimen. The biggest crack gains the upper hand, grows the fastest, and finally leads to fracture after 381,000 load cycles. The first test is finished. The material tester removes the fragments cautiously and inspects the fracture surfaces. At first glance, the fracture surface looks unimpressive. A closer look reveals two regions: the rather dull, predominantly flat fatigue crack propagation area and the rough residual fracture area. The residual fracture area results from the final catastrophic rupture. The fatigue crack propagation area has developed during the cyclic growth of the fatigue cracks starting at the surface of the specimen. What does the fatigue crack propagation area look like at higher magnification? One of the fragments is carefully placed on the specimen stage of our scanning electron microscope. Now we can investigate the fatigue crack propagation area in detail. In some places, but not everywhere, parallel grooves and ridges can be seen, the so-called fatigue striations. Each groove and each ridge has been formed by an individual load cycle, a typical phenomenon. Of course, now we want to know how many load cycles this material can endure with other loads. For this purpose, the material tester picks the next specimen from his supply and installs it into the fatigue testing machine. He chooses a higher alternating load for the second specimen, a tensile force of 7.5 kilonewtons and a compressive force of 7.5 kilonewtons. Under the increased load, the specimen is only able to withstand 43,600 cycles to failure. The third specimen is only tested with a cyclic load of 6.5 kilonewtons. Under this reduced load, it does not break even after 3 million load cycles. Additional specimens complete the series of measurements. Some of the specimens are tested with the same load we've already used. In this way, we get an impression of the range of scattering. To compare materials in a fair way, the different cyclic loads are converted to the respective stresses acting in the specimen. In this case, the stress alternates sinusoidally around the mean value, which is termed mean stress sigma m. In this series of tests, the mean stress is 0. The stress amplitude is labeled with the symbol sigma a. For graphical representation, the SN diagram is used, also termed Wöhler diagram. In an unusual manner, the predetermined variable is plotted upwards on the y-axis. It is the stress amplitude sigma a. And the result of the test, the number of cycles to failure n, is plotted to the right on the x-axis. To fit small and large numbers into the diagram, the x-axis is not scaled linearly, but logarithmically. Was loaded with 7 kilonewtons. This corresponds to a stress amplitude of 248 newtons per square millimeter. Under this stress amplitude, it broke after 381,000 load cycles. The second specimen was loaded with 7.5 kilonewtons. This corresponds to a stress amplitude of 265 newtons per square millimeter. Under this stress amplitude, it broke after 43,600 load cycles. And these are the results of the other specimens which have been tested by us. When additional specimens are tested and the results are displayed as a curve, it becomes clear that this material will not break below a certain level of stress amplitude, even after a very large number of cycles. This stress level is termed fatigue limit sigma capital A. For most steels with body-centered cubic structure, the fatigue limit is reached after 10 million load cycles at the latest. It must be noted that the experimental results scatter considerably. Therefore, instead of a sharp curve, a statistically defined scatter band is commonly used. Of course, most users don't load has to go into the test hole at regular intervals. Experienced staff use ultrasound to examine special components, especially the wheel set axles, to check whether they are still in perfect condition. Aircraft are also inspected for fatigue cracks at reasonable intervals. This helps us to depart for air travel without worry and land again safely. Fatigue test.
Okay, the second video show us how to obtain the SN diagram. Okay, so relating to the question of Bella previously, we must know that those SN diagram is obtained for completely reverse bending. Okay, so for one type of loading, specific loading. So it can axially loading like this and fully reversed. Fully reversed mean the sigma maximum will have the same magnitude with minimum, only different on the direction. So the average will be 0. So this kind of load that that used during the test in the laboratory. Okay. So how if the same specimen given different type of loading? So for example, like this. It has similar amplitude. So the amplitude is equal. But it has different sigma average. The question is, can we use this data obtained from the different type of loading? Does this kind of loading will have the similar response from the material? Of course not. So how we can use this provided data, although we have different type of load? Okay, so first we call this the fully reverse or completely reverse stress. And then here we have reverse, and we have another here. This is fluctuating. Okay, let's see this first. Sorry. Okay, so we call this reverse stress, and this is repeated stress, and this is fluctuating stress. Okay, so for the laboratory measurement, we use reverse stress, but in the design or in the application, we may found other type of cyclic stress. It can be repeated stress or fluctuating stress. So Goodman, Soderbergh, and other theory facilitate the tools to to estimate or facilitate the calculation for this different type of loading, so that we can still use the SN curve obtained by this experiment. Okay. Okay, please have a minute here. So for example, for Gerber, okay, Gerber. Gerber formulate this kind of stress transformation. This is the amplitude, and this is the endurance strength, and this is the safety factor, factor of safety, minus sigma average or sigma mean. Sorry, we will use mean for the average here, over sigma ultimate times the factor of safety. Okay, so here Gerber want to facilitate the conversion. Okay, so if we have any type of loading, as long as we can describe the sigma m or the average and the sigma amplitude, then we will able to use the standard SN curve for that material. Okay. So for example here, this is the real loading. Okay, so this is the given load. For example, it has repeated stress here. So that here we have sigma m, or the average, is equal to sigma max here divided by 2, because we have sigma min here equal to 0. And here we have the amplitude is equal with also sigma m equal to sigma m. Okay. Sorry. The amplitude is sigma maximum also divided by 2. Oh, no, sorry. So this is sigma min is sigma max plus sigma min over 2, and sigma amplitude is sigma max minus sigma min. Okay, so for this given load, we can describe the load using the average stress and its amplitude. Okay, and on the other side, we have for this material, we have the SN curve of this material. And it's maybe like this. So for this type of material, we have here the endurance limit. The endurance limit for this material. This endurance limit measure the maximum given load that can extend the life cycle of the material up to infinity. So below this load, the material will never fail due to the fatigue. Okay. So this endurance strength define that this is the limit of the maximum load that can hold by the material, so that this material will not fail due to fatigue. Okay. And this material also have the ultimate stress as the in a static failure. It also has the ultimate strength as mentioned in static failure. Okay, so now we can write for the safety factor here, we can write this equation. So this is sigma min, sigma ultimate, sigma amplitude over sigma endurance. Okay, and now we want to plot, if we use this equation to plot the graphic, where the axis for the horizontal is the static failure of the material. So here we have the ultimate strength here, the ultimate strength of the material, and here this is for static load, and this is for fluctuating load. Okay, so this is for cyclic loading. So here we have endurance limit here. Endurance strength of the material. So using this equation, Gerber give us the parabolic line, like this, which mention that inside of this diagram, inside of this curve, the material will not have fatigue. So it will save from fatigue. But outside of this curve, it will have a limited life. Okay, so inside this curve, it has infinite life because it never has failure fatigue. No fatigue failure. But outside, the element will have a limited cycle. Okay. And we must calculate this cycle to estimate the lifetime of the product. Okay, so this line is belong to Gerber. And Goodman also has another line different with Gerber. Okay, different with Gerber. Because Goodman has different equation. For Goodman, he described that the amplitude of the fluctuating stress is equal to the endurance limit. Okay, so this is the allowed amplitude stress on the given load should be equal to the endurance strength over the safety factor, and it has here 1 sigma m. This is the ultimate S like this. So it will be linear equation. Okay. So because Goodman has linear equation which relate the endurance strength with the ultimate strength of the material, then we just take a linear line from the endurance to the ultimate strength of the material. And it gives us a description that below this line, the specimen or the component will have infinite life, doesn't have fatigue failure. But above this line, uh, it will have a limited cycle, similar with Gerber, but has different criteria. So Gerber, Soderbergh, and Goodman actually is a scenario or criteria for failure of the material. And how about that I provide in our classroom, or maybe we can watch them together for 1 or 2 problem solving. Okay, so for Bella and others, the conclusion is that Soderbergh, Goodman, and Gerber is a criteria to evaluate the performance of a component at a given load. Whether this component will have finite life or infinite life. Okay, how about that? That's answer.
I think it's already very clear, sir. Thank you, sir.
Okay, so please do not forget to make a screen capture for this note so you can write later. But actually, I prepare a lecture note for this kind of filler analysis. So you can download it later in the classroom. Okay, so any other question here? Okay, for Soderbergh, why he used yield stress instead of the ultimate? Do you know the reason why? Or when we have to use Soderbergh instead of Goodman? Because
I
it
think
has
it's
different criteria.
when we don't want the deformation.
Pardon, can you explain it again one more?
I think why is using yield stress is because the user avoid the deformation.
Avoid the deformation. Oh, okay. So you mean that if the user or the designer doesn't allow plastic deformation, so he must use the Soderbergh criteria. Is that right? Is that
Yes,
what you mean?
I think that.
Okay. So what kind of material that can has plastic deformation? Is it ductile material or brittle material?
Yes, tactile.
Ductile. So okay. So let's take this. So for Goodman, if we use the brittle material, then we can choose Goodman standard or Goodman criteria because it doesn't have yield strength. The material will be fractured on the brittle scenario. But for ductile material, we will use Soderbergh because it can deform plastically. So we have to avoid that kind of deformation. Is that right, Hafiz?
Yes, I think so.
Okay, how about the others? Do you have any other opinion? Why we have Sigma Ultimate and Sigma?
Sir,
Yes.
I'd like to ask. So
Please.
if the tactile is given the uh, fatigue, so it will deform or until it breaks. I mean, if the failure is the material is ductile, will the material will break or only deform if you use the ductile?
It will break actually. It never has necking. Different with static failure. During static failure for yield material, it will deform plastically and the area will decrease or we call necking prior to the failure. But for this cyclic loading, there is no that kind of deformation. It will be suddenly brittle fracture. But what we have here is that for this criteria for Soderbergh, he put a very strict or lower strength that can be handled by the specimen because it based on the yield strength. As we know that for the yield strength, it always less than the ultimate, right? So when we choose this criteria, okay, when we choose this criteria, we want to make sure that before the fracture happened, it never initiated by the yield deformation. So, in conclusion, if we choose the Soderbergh criteria, then we have very strict safety criteria for this object or this element because it predicts the failure earlier than the other criteria. Okay, so okay, maybe later we can give you a good argument about these three criteria. How we choose Soderbergh, Goodman, or Gerber criteria in our design relating with the type of material that we use. Okay, so for that, you can check this video. We have filler criteria, or we just watch it together here and then discuss again, just like previous one. Okay, so please has a moment to watch this video with me.
For many applications, fluctuating stresses are not completely reversed stresses. A couple videos ago, linked below, we looked at different example plots for alternating stresses where the mean stress is not zero. Yet most of the examples for SN diagrams, Morin factors, and fatigue stress concentration topics have used completely reversed stress, where the mean stress is zero. Think about most of the applications that use springs, which we will also cover in detail in future videos. A simple spring inside your retractable pen or clicky pen is already subjected to a certain load to keep it in contact with the button that you press to bring out the nib of the pen. As you press it to expose the tip to right, the spring is compressed even further, and when you let go, the spring is only partially relaxed. Press it once again and you reach the same level of compression, only this time to reach a more relaxed state after letting go. If you think of the valve springs in a fuel engine of most cars, we see something similar. The spring is already compressed, and as the engine and piston cycle, the spring is compressed over and over, hundreds to thousands of times every minute. In the same way, a spring inside the suspension of a car is already preloaded with a fraction of the weight of the car, and as you drive and hit speed bumps or potholes, the compression fluctuates around an already loaded state. It's easy to see how for a clicky pen it is reasonable to ignore intermediate peaks. And no matter how complex the operation is, there is always ways to obtain reasonable life estimates. More on those cumulative fatigue damage concepts later. Regardless of the specific application and how complex the operation is, understanding fluctuating stresses that don't revolve around a mean stress of zero is very useful for fatigue calculations. The first concept we need to understand is that a fluctuating stress that goes from 0 to 2 sigma is not the same as a stress that goes from negative sigma to positive sigma. Even though the alternating stress value is the same, sigma, case 1's mean stress is sigma, while case 2's mean stress is 0. And case 1 is also not the same as a stress that goes from negative 2 sigma to positive 2 sigma, even though the maximum stress in both cases would be 2 sigma. We can say that case 1 is more taxing than case 2, because the overall maximum tensile stress in 2 never comes close to that of 1. But case 1 is also not as taxing as case 3 because in case 1 we only have a maximum stress and tension of 2 sigma, while in case 3 we have both tension and compression of 2 sigma. Let's think about steels for a minute, and let's recall that the endurance limit is defined for 1 million cycles and above. If I have a plot for alternating stress on the y-axis and mean stress on the x-axis, from everything we've covered so far, I know that for a completely reversed stress, which has a mean stress of 0 and an alternating stress of sigma a, meaning x equal to 0 and y equal to sigma a, The part would fail when the alternating stress value is just above the endurance limit. Of course, this is true for 10 to the 6 cycles. The part would be required to be subjected to a higher stress if the number of cycles was reduced. For 10 to the 5th cycles, the alternating stress can be higher and equal to the fatigue strength for 10 to the 5th cycles, for it to fail exactly at 10 to the 5th cycles. And so on and so forth. Regardless of the number of cycles, if the alternating stress is 0, which means the stress is just constant and equal to sigma m, and therefore it does not fluctuate, that is, for y equal to 0 and x equal to sigma m, I know the part will fracture when sigma m is equal to or exceeds the ultimate strength. These are called the constant life curves on the fluctuating stress diagram. There are situations where you know a part will only operate for a known number of cycles, situations for which you will want to calculate the factor of safety and therefore the fatigue strength for a specific number of cycles, like we've been doing in previous videos. But for many applications, you just want to design a part to have an infinite life. So we'll focus on endurance limits for now, and up to this point we would assume that any combination of sigma A and sigma m within this triangle would not cause the part to fail. The factor of safety would be calculated just like we did with static loading as the ratio between the length of the line from the origin to the safe line and the length of the line from the origin to the stress state, which follows the same expression that we derived when looking at the failure criteria for static loading. Since for many applications exceeding the yield strength is considered failure as it would cause plastic deformation, we add an extra boundary line for the combination of sigma A and sigma m that when added together, which will happen at some point during the stress cycle, would exceed the yield strength, which happens whenever a stress state is located above a line bounded by Sy in the y and x axes. This would of course change what I just explained on how to calculate the factor of safety, creating two different regions. Fortunately for us, the fatigue failure criteria curves that follow what experimental data yields are already functions that more easily mathematically define the factor of safety. We have straight lines for Goodman, Morrow, and Soderberg, where Soderberg uses the yield strength, Goodman uses the ultimate strength, and Morrow uses the true fracture strength. Remember that true fracture strength that I talked about several videos ago? This is where we use that. But these are too conservative. Lab results show that curved or elliptic plots fit the data better, like the Gerber or the ASME elliptic criteria. One criterion that does not simply attempt to fit experimental data is the Smith-Watson-Topper criterion. It uses theoretical bases and strain life methods to delineate the boundary. And since it doesn't converge to 0, it's usually used in combination with the yield strength to yield strength line we discussed before. Mathematically, there will be a design equation for each one of the criteria. We already know what the straight lines look like, with once again Goodman using the ultimate strength, Morrow using the true fracture strength, and Soderberg using the yield strength. For Gerber and ASME elliptic, the definitions are pretty easy, where you have a squared term for the mean stresses in Gerber, and each one of the two terms squared for the ASME criterion. By using these function definitions and carrying out a similar procedure to the one I explained before for calculating the factor of safety, we obtain the expressions for the factor of safety for each one of the criteria. Let's take a look at a quick example now. The pedal of a piano is a part that is pressed on many times during its lifetime. As you press down, the pedal swings around the hinge that initiates the movement of the rest of the mechanism. When the motion stops, but the load is still there, the pedal is effectively subjected to bending. Even though the motion of the opposite side is in the upward direction, the reaction force is going downward. And if we were to look at the cross-section of the pedal, we would see that it's not a solid rectangle. Of course, we can do all the calculations to find the second moment of area, for example. But for the purposes of this example, which focuses on fatigue failure criteria, we will simplify it as a rectangle of 1 by 1/4 of an inch. And I know that the radius of the notch around the hinge is equal to 1/32 inches. Assuming the pianist puts a lot of their weight on the pedal when playing intensely, we will assume a load of 40 pounds. I would like to estimate the fatigue factor of safety based on achieving infinite life, using for example the Goodman and the Gerber criteria. Remember once again that all of these problems have two independent processes. The first one has to do with the strength, or in general the material properties, and the second one has to do with the stresses. Let's begin with the strength, or in this case, the endurance limit, since I'm interested in the infinite life. A piano pedal is probably made out of brass, But let's assume it's just a steel, so that we can use the plots and equations that we've grown familiar to. The ultimate strength of the steel I'm using is equal to 77.5 KSI. Since I'm not trying to find a fatigue strength, and therefore I don't need the SN diagram, I won't be needing to find the F coefficient for the F times SUT term. I just need a first estimate of the endurance limit, SE, and a more accurate one using the marine factors. As with a real brass pedal, the surface finish would probably be a polished one, and therefore the surface factor would be equal to 1. Using the equivalent diameter equation for a rectangular cross-section, I would find that the equivalent diameter is 0.404 inches. If I use that value, which is between 0.3 and 2 inches, to calculate the size factor KB, I would find a value of 0.969 for it. Since the loading the pedal is subjected to is bending, Kc would be equal to 1. And since the temperature will probably just be the room temperature, and my calculations are looking for a factor of safety, and therefore I don't need the reliability factor, both Kd and Ke will be equal to 1 as well. A better estimate for the endurance limit using the marine factors yields a value of 37.5 KSI. And this is half of what the problem was asking for, since I now have the endurance limit and the ultimate strength, the two properties that I will need for my factor of safety calculations. The second step is regarding the stresses. And here I'm trying to identify the values for the alternating stress and the mean stress. And this is mostly mechanics of materials with a little bit of fatigue when trying to find the fatigue stress concentration factor. I know that the maximum stress is equal to the stress concentration factor for fatigue times my over I. For a notched rectangular bar in bending like this one, I will need the W over D ratio and the R over D ratio, where W is 1/4 of an inch, the notch radius 1/32 of an inch, and therefore D 3/16 of an inch, which result in ratios of 4/3 and 1/6, or 0.16 repeating. Looking at the value for the static stress concentration factor Kt, I would find a value of 1.7. And if I look for the notch sensitivity value for a material with an ultimate strength of 77.5 KSI and a notch radius of 1/32 of an inch, I would find a notch sensitivity of roughly 0.7. Using these values and the expression we obtained during the last video, we find a fatigue strength concentration factor Kf of 1.49. With the moment at the notch of 3 inches times 40 pounds, the maximum stress value would be equal to 17.16 KSI, which means that the mean stress and the alternating stress both have a value of 8.58 KSI. All there is left to do is use the expressions to calculate the factor of safety following the Goodman and the Gerber criteria. For Goodman, we would obtain a factor of safety of 2.95, and for Gerber, we would obtain a value of 3.66. Looking back at the fluctuating stress diagram with the different criteria, it makes sense that the Gerber value for the factor of safety is slightly higher. As always, make sure to check out the links in the description of this video. And in the next video, we'll cover some topics related to shaft design for stress, which is basically applying everything we've learned about fatigue for the specific case of a
Okay, it looks like that this video is jumping to the example, okay, but not discuss about the fatigue filler. The previous videos should be discussed about this, and I think I already make our own video uh, about how to do the fatigue filler analysis. So please watch this. Terima kasih masih bersama saya Yohanes dalam kuliah elemen mesin. Kali ini kami akan menyajikan sebuah tutorial tentang perancangan sebuah elemen mesin yang dikenakan beban fluktuatif dan diharapkan elemen ini memiliki umur yang lama atau aman dari kegagalan fatik. Tutorial ini adalah salah satu dari rangkaian tutorial untuk kegagalan fatik yang sudah kami persiapkan. Pada tutorial kali ini, kita diminta untuk merancang ketebalan sebuah plat dengan geometri yang sudah diketahui dan beban kerja yang sudah diketahui, seperti yang ditunjukkan pada gambar. Plat dengan lebar 50 mm mempunyai lubang di tengahnya sebesar diameter 10 mm. Beban yang bekerja padanya adalah beban fluktuatif, reverse load, berupa tarik tekan sebesar 32 Newton. Jika material plat dan beberapa faktor koreksi diketahui, serta faktor safety juga diberikan pada soal, maka berapakah tebal plat agar plat ini aman terhadap kegagalan fatik? Atau dalam kata lain, dia memiliki infinite life. Umurnya panjang sekali, tidak pernah gagal karena kelelahan. Pada prinsipnya, agar komponen mesin tidak mengalami kegagalan fatik, maka beban yang bekerja harus berada di bawah nilai endurance limit dari komponen tersebut. Mari kita bersama-sama menyelesaikan contoh kasus ini. Tujuan utama dari perancangan ini adalah menentukan ukuran tebal plat agar plat tidak mengalami kegagalan fatik ketika dibebani dengan beban fluktuatif sebesar 30 kN. Kita bisa menentukan tebal plat setelah mengetahui kekuatan endurance dari material tepat tersebut. Maka langkah pertama untuk menyelesaikan permasalahan ini adalah dengan mengetahui berapa endurance limit dari plat. Plat dibuat dari steel. Kita bisa melihat endurance limit untuk material steel atau menggunakan pendekatan lain, seperti yang digunakan pada contoh soal ini. Di sini, endurance limit untuk steel didekati dari tegangan ultimate-nya. Didefinisikan, endurance limit adalah separuh dari kekuatan tenselnya atau tegangan tenselnya. Jika kekuatan ultimate dari plat adalah 440 MPa, maka endurance limitnya adalah separuhnya, yaitu 220 MPa. Namun perlu diingat dan diperhatikan bahwa
Pak, sepertinya termute ya, Pak.
Oke, terima kasih. Ya. So, one thing we have to know about the characteristic of the material is that for several material, actually for steel, the endurance limit before the correction factor applied. So usually we use this notation. This is the ideal endurance limit obtained from the test in the laboratory. Sorry. Okay, first we have the endurance test of the material. So for this material, we check on the textbook or standard handbook, and we can find that this material has this kind of endurance strength. Okay, for this defined material, it has a certain endurance strength. But this graphic, this SN curve is ideal. It is only applied on the laboratory. And the specimen used is a cylindrical, a dog bone cylindrical like this. But in application, it can be a plate, beam, and any other geometry. So the first question is that, is the geometry has an effect on this endurance strength or endurance limit? Yes, of course. So that's why we have to put the correction factor. Okay, we have to put the correction factor. So the endurance strength should be equal with the endurance strength obtained from the laboratory multiplied the geometrical correction factor, or we call this the shape factor. And in the laboratory test, the surface finish also has influence on the endurance strength of this material. Okay, so for the standard specimen, it is polished So the surface finish is very good, but in actual condition, the surface finish may be different. It can be rougher than in the laboratory. So we have to put here the surface finish factor again, another factor here. So not only surface finish and the shape of the shape and size of the specimen, there are many other factors here applied. The type of loading, for example, because in the laboratory maybe it tested using axial or bending, but in the practical it can be torsional. So it is a different type of load. So how we can apply this standard with different type of load? We have to put another factor here. So we will discuss later about the influence of each factor. But first we have to know that we cannot directly use the data from the material handbook, which describe the standard laboratory test on a real application. We cannot directly use it for the real application. Okay, for example, in this case, we have plate with hole and we have a different surface finish. Okay, so that's the first note for this tutorial. And next for the endurance strength. Okay, so for endurance limit, for several material, usually for steel, it can be approached or can be predicted or estimated from the ultimate tensile. Okay, so the idea is many engineers ask, is there any relation between the endurance properties of the material with the tensile test of the material? If there is correlation between the ultimate tensile and endurance stress, then we don't need to do uh, the experiments, which is costly in time and other resource. So we just need only single test, that is tensile test only. Then we can predict the endurance. That's the main idea. But unfortunately, not all the material can be predicted like that. But for steel, we have some estimation. So we can estimate that the endurance of the steel is half of its ultimate strength, which is this ultimate strength obtained from the tensile test. Okay, so without doing the SN curve, we can estimate the endurance limit for the steel. Okay, please make a note, only for steel. Okay. Okay, so here we have some correction factor applied on this equation. We have the ultimate tensile here known as 440 megapascal, so that we can estimate that the endurance limit is half of it, so 220 megapascal here. But we have some correction factor about the size, surface finish, and stress concentration, and also for reliability factor as mentioned here. So all those constants will modify the endurance strength of the material. Okay, so let's continue this tutorial. bahwa angka endurance limit ini adalah angka endurance limit ideal dalam skala uji laboratorium, sehingga di sini ditandakan dengan tanda aksen, tanda kutip. Spesimen uji untuk skala laboratorium pasti berbeda dengan material yang digunakan pada praktiknya. Dalam praktiknya, perlakuan pada permukaan spesimen bisa berbeda, sehingga ada faktor koreksi surface finish. Kemudian ukurannya pun juga memiliki pengaruh. Maka ada faktor koreksi untuk ukuran, dan sebagainya. Maka setelah kita menentukan endurance limit skala laboratorium ini, SE aksen, kita harus mengalihkannya dengan faktor koreksi tersebut. Pada slide ini ditunjukkan faktor koreksi surface finish. Bagaimana cara mencarinya? Lihat pada gambar kanan bagian atas. Ada tabel surface finish faktor, dengan sumbu X-nya adalah kekuatan tenselnya, kemudian sumbu Y-nya adalah surface finish faktor. Terdapat beberapa garis kurva di sana yang menandakan bagaimana spesimen itu diproduksi. Nah, data untuk plat yang kita gunakan dalam desain komponen ini adalah hot roll dengan kekuatan tensel 440. Maka kita bisa menarik garis dari angka 440 ke atas sehingga menyentuh kurva hot roll, kemudian kita tarik ke kiri untuk mencari surface factor, seperti yang ditunjukkan oleh garis merah. Maka kita bisa mendapatkan angka surface faktornya adalah sebesar 0,67. Kemudian berikutnya perhatikan pada plat terdapat sebuah lubang dengan diameter 10 mm. Untuk skala laboratorium tentu saja tingkat keyakinan kita terhadap properties material ataupun terhadap beban yang bekerja. Misalnya, apakah benar kekuatan material adalah tepat seperti yang diberikan pada tabel data sebesar 440? Atau tingkat keyakinan kita pada beban yang bekerja, apakah benar bisa dikendalikan dalam rentang plus minus 30 kN? Nah, di sini kita mengambil tingkat keyakinan untuk desain ini adalah 90%. Sehingga kita harus menambahkan faktor koreksi untuk reliability ini sebesar 0,897 seperti yang ditunjukkan pada tabel bagian kiri bawah slide. Faktor koreksi yang perlu diberikan berikutnya adalah faktor koreksi konsentrasi tegangan. Kita lihat di sini plat memiliki sebuah lubang, di mana area di sekitar lubang itu akan mengalami konsentrasi tegangan. Seperti yang disampaikan di dalam teori, bahwasanya discontinuity pada material akan menimbulkan konsentrasi tegangan. Dan di sini terjadi discontinuity geometri. Untuk menentukan besarnya stress concentration factor, maka di sini diberikan sebuah grafik. Ada beberapa grafik untuk mencari stress concentration factor ini, jadi kita harus memilih salah satu dengan geometri yang bersesuaian dengan komponen yang akan kita desain. Nah, pada gambar kurva di sebelah kanan slide ini, kita memiliki sebuah plat dengan lebar W dan diameter lubang D. Maka kita dengan data yang kita miliki dari geometri plat, diameter lubang adalah 10 dan lebar plat adalah 50. Maka kita memiliki perbandingan D terhadap W adalah sebesar 0,2. Kemudian kita menarik garis dari titik 0,2 pada sumbu X ini ke atas hingga menyentuh kurva. Kemudian kita tarik ke arah kiri untuk mendapatkan nilai faktor konsentrasi tegangan. Dan di sini kita dapatkan nilai sebesar 2,51. Lubang pada plat juga dapat diartikan sebagai sebuah takian atau cekungan. Takian atau cekungan ini akan mengurangi kekuatan dari material. Nilai sensitivitas kekuatan terhadap takian ini ditentukan oleh grafik di sebelah kiri slide, di mana sensitivitas terhadap takian ditentukan oleh ukuran radius cacat. Di sana kita bisa lihat beberapa garis yang mewakili jenis material tertentu dengan kekuatan tertentu. Kita lihat ada sebuah garis untuk baja dengan kekuatan tarik 400 MPa, dia asimtot mendekati angka 0,8 ketika radiusnya bertambah besar. Maka di sini untuk radius 5 mm kita anggap node sensitivity faktornya Q-nya adalah 0,8. KT atau faktor konsentrasi tegangan itu adalah kompensasi dari perhitungan untuk beban statik. Nah, sedangkan sekarang yang kita hadapi adalah beban dinamik, sehingga kita harus mengkonversi faktor konsentrasi tegangan ini menjadi faktor konsentrasi fatigue. Faktor konsentrasi fatigue atau kelelahan ini dipengaruhi oleh node sensitivity dan faktor konsentrasi tegangan untuk beban statik. Di sini bisa kita hitung, KF kita dapatkan sebesar 2,208. Pada perhitungan selanjutnya, KF ini bisa langsung digunakan sebagai pembagi dari endurance limit material. Atau KF ini bisa diganti dengan KD yang merupakan kebalikan dari KF. Tidak perlu bingung, ini hanya perubahan notasi saja. KD sama dengan 1 per KF. Tujuannya adalah agar persamaan untuk menentukan endurance limit aktual itu lebih sederhana, tidak ada pembagi lagi. Semua faktor adalah faktor pengali. Nah, sekarang sudah lengkap semua faktor yang berpengaruh terhadap endurance limit aktual. Kembali, kami mengingatkan bahwasanya di sini faktor konsentrasi tegangan dan faktor-faktor koreksi yang lain yang sudah kita tentukan itu diperlukan untuk mengkoreksi endurance limit ideal skala laboratorium untuk mendapatkan nilai endurance limit di dalam praktek yang sesuai dengan kondisi perancangan. Seperti yang ditunjukkan pada persamaan berikut, endurance limit di dalam praktek desain adalah sama dengan faktor konsentrasi dari yang semua sudah kita cari dikalikan dengan nilai endurance limit untuk skala laboratorium. Di sini ternyata kita lihat faktor modifikasi atau faktor koreksinya nilainya semua kurang dari 1. Sehingga secara akumulatif dia akan memperkecil nilai endurance limit dari yang diperoleh dari skala laboratorium. Yang semula 220 sekarang menjadi seperempatnya saja, menjadi 50 megapascal. Namun perlu diingat, endurance limit ini masih mengikuti beban seperti yang ada di dalam laboratorium SA aksen, yaitu untuk bending, untuk beban bending. Padahal di sini, untuk kasus kita kali ini, beban yang bekerja adalah beban aksial. Tentu saja nilainya akan berbeda, sehingga perlu dikoreksi sekali lagi. Seperti yang bisa kita lihat pada perhitungan bagian kanan atas, endurance limit untuk beban aksial adalah 80% dari endurance limit untuk beban bending. Hal ini masuk akal, karena untuk beban bending, distribusi bebannya tidak merata. Sedangkan untuk kasus praktik kita kali ini, semua beban 30 kN bekerja merata di seluruh penampang pelat. Angka 0,8 adalah ketetapan yang diberikan. Sehingga di sini, endurance limit untuk beban aksial pelat setelah dikoreksi, nilai akhirnya adalah 40,7 megapascal. Ingat, arti dari endurance limit ini adalah batas kekuatan maksimum yang masih diizinkan oleh material untuk bisa selamat dari kegagalan fatigue. Di dalam perancangan ini, selain ada faktor reliability atau keyakinan kita terhadap semua faktor yang mempengaruhi desain ini, kita juga menambahkan angka keamanan, safety factor. Okay, so the tutorial is stopped. Maybe the video is not complete yet. I have to check it. But from this video, we can grasp the information that for the real application, of the fatigue analysis, we have so many correction factor here. So now I want to show you each of them, each of the correction factor given for the endurance limit. So let's take a look this slide. Okay, so I will stop sharing for a while and change. Okay, so the main purpose of this correction factor is to adapt the practical application to the laboratory test result. So in that way, using this correction factor, we can use the data obtained from the laboratory, even though the real condition is different. Okay, so first, okay, the first correction factor will be the type of loading. Okay, so here Here we have several correction factors. The first is KB, which give correction for rotating bending load, because in the laboratory we also use the bending load. So this value of KB is equal to 1, because the real condition and the laboratory testing is similar. Both of them are in bending load. But for axial load, just like in our case for plate, which given a reversal axial load, then we need to put a correction factor there. We will give the correction factor of 0.8. So for the endurance limit that we will use in calculation, we have to put this Ka times the endurance limit obtained from the test, from the laboratory test. So you have to remember that all the factor always less than 1 means that it reduces uh, the strength obtained from the laboratory. Okay, so for real condition, the endurance limit always lower than obtained from the laboratory because of this. Example is joint in we have 0.5 for ductile material, but for brittle we have 0.8. So that's how the type of loading influence the endurance strength of the material. Okay, so next we have here the surface finish effect on the endurance strength. And all of this information is related with steel material. So for other type of material, we have to find the correction factor for the type of load and also the surface finish factor. And this is related with the steel. Okay. For steel, here we have some technique or surface condition. Okay. For the mirror polish, if you polish the surface of the steel until it very shine just like a mirror, so you can see your shadow on the surface, then it will have the perfect ideal condition, just like we used in the laboratory test. So the correction factor will be 1 for every type of, for every strength of material. But if you machined using lathe machine, hanya dibubut saja, then the correction factor will be reduced with the increase of the ultimate tensile strength. So the correction factor will be reduced. If we use a larger ultimate tensile strength, then the correction factor for the machined element will be decreased from 0.9 up to 0.7, about 0.7. Okay. And when the surface finish is rougher, semakin kasar, then the surface finish factor becomes smaller, means that the endurance limit will decrease, will be dropped because poor surface finish. Okay. And also have other factor that we consider in our design. Okay, so to check those, to check how to say, to check the effect of those factors, just uh, watch the video, the previous video, okay, and you can use the diagram given in the textbook to find the value of each this factor. Okay, so for other tutorial, you can watch by yourself, and I will prepare the forum for the discussion there, and even you can ask the question about how to solve the problem. But first, you have to work by yourself, and you can post it in the forum if you have any problem how to solve that question or problem. Okay, so first please watch all the video to have a good understanding about the concept of the fatigue analysis, and then you can try yourself to solve the problem on the textbook. And if you have the problem about the concept or about the question or the problem in your exercise, then please post it in the forum. So today I have free time, so I can follow the forum until the end. Okay, so just write your question about this fatigue topic in the discussion. Okay, before we end this lecture, do you have another question?
Excuse me, sir. I want to ask you about something.
Yes, Sultan.
On your example, there is we need to substitute some another variable or not, or just the position is the same, but we just to change the symbol. Apakah begitu, Pak?
Okay, so do you mean that if we change the load into torsional load, then how about the correction factor? Is it the same? We use just like the axial, or we need to put another correction factor? Is that what you mean? So then,
Yes, sir.
okay, so just just like I mentioned previously, that for torsional and shear load, for ductile material, we use correction factor of 0.5. But for brittle material, we use 0.8. For axial material, we have 0.8 also. Is that what you mean, Sultan?
Oh, yes, sir. So just the difference just on that coefficient, yes, sir.
Yes, only the coefficient.
Okay.
So we just choose it with the type of load. Okay. So I'm sure that you have a lot of questions, and your friend also. I'm sure. And for today, I'm free enough, so I can answer your question in the forum. So please be active in the forum, okay? And put all your question there, because we have limited time in Zoom here, and I'm sure that take too long on this Zoom will not guarantee that we can fully understand about the concept. So that's why I choose to discuss in the forum. Okay. So if you don't have any other question, then
Sir, sorry, sir.
yes, Edgar, please. Seperti yang saya bilang, saudara boleh khawatir dengan hasil evaluasi saudara di kuis 1 dan 2. Karena seperti yang kalian sampaikan kemarin, ada beberapa mispersepsi tentang istilah, tentang apa yang itu bukan substansi sebenarnya, gitu ya. Karena cuma istilah saja. Saudara boleh khawatir tentang hasil yang kemarin, tetapi saudara masih punya banyak kesempatan. Kita masih punya banyak cara dan masih punya banyak waktu, sekitar 4-5 kali pertemuan untuk memperbaikinya. Gitu ya. Jadi di setiap kuis atau di setiap bentuk evaluasi yang lain, saya upayakan itu sebagai kompensasi atau sebagai perbaikan untuk kuis yang lalu. Jadi nanti kalau ada reading kuis, kemudian ada self assessment, itu tolong dikerjakan. Karena itu nanti yang akan membantu untuk memperbaiki nilai kuis saudara. Nah, kalau nanti kalau terpaksa itu tidak bisa dievaluasi menggunakan cara tadi, maka saya akan sediakan waktu khusus tambahan untuk memberikan remedi kepada kalian terkait kompetensi yang belum tercapai. Saya tidak ingin ada yang gagal di mata kuliah ini, tetapi tetap dengan cara bukan memberikan nilai, tetapi memberikan kesempatan untuk evaluasi kembali. Berulang-ulang pun bagi saya tidak masalah. Karena kita punya classroom yang bisa diakses juga berulang-ulang, gitu ya. Jadi selama kalian masih kuliah elemen mesin di semester ini, kalian semuanya masih punya kesempatan untuk memperbaiki nilai. Begitu ya Edgar ya. Tapi kalian tetap boleh khawatir loh, karena kalau kesempatan-kesempatan itu tidak digunakan dengan baik, kemudian kalian tidak berlatih, maka sampai habis waktu nanti mungkin ada kompetensi yang tidak terpenuhi. Nah, kalau seperti itu saya tidak bisa menolong lagi. Gitu ya Edgar ya?
Baik, Pak.
Ya. Evaluasinya. Jadi karena kita pakai OBE, OBE yang normal itu seharusnya memang ada evaluasi setelah tengah semester, dan kalian bisa drop mata kuliah jika evaluasinya buruk, gitu ya. Tetapi kuliah kita ini tidak normal karena kita menggunakan sistem online terus-terusan, dan saya yakin pemahaman itu tidak akan sebaik kalau kita ketemu di kelas. Sehingga saya agak mengingkari yang aturan yang harus ngedrop jika evaluasi buruk. Tapi saya pilih untuk terus memberikan kesempatan kalian memperbaiki hasil ujian selama semester ini berlangsung. Begitu ya. Yang perlu kita lakukan adalah untuk tetap aktif di setiap sesi kalau diskusi di kelas begini, tolonglah kalian menyampaikan pertanyaan. Seperti tadi sudah ada Bella ya, selain Edgar dan Sultan ada Bella, ada siapa tadi? Faiz ya, ada Faiz gitu ya. Nah, itu bagi saya nilai tambah itu. Berarti memang sedang belajar. Nah, yang belum bertanya, belum mengungkapkan komentarnya, kalian mempunyai kesempatan di forum. Nah, kesempatan di forum itu gunakan untuk memperjelas konsep, kemudian untuk asistensi kalau saudara mengerjakan soal-soal tapi ada masalah, tunjukkan di sana masalah kalian. Jadi dengan itu saya tahu kalau kalian sedang berlatih. Nah, kalau kalian tidak menunjukkan suatu kasus yang kalian tidak bisa mengerjakannya, maka saya anggap tidak ada masalah, atau saya anggap saudara tidak berlatih, gitu ya. Jadi tolong ya, mungkin bentuk perbaikannya tidak ujian resmi, tetapi melalui diskusi di kelas seperti ini, atau melalui diskusi di forum. Ya, atau bentuk asesmen yang lain, bisa reading quiz atau self-assessment. Begitu. Jika ada yang ingin berkomentar, silakan sebelum saya akhiri. Jika tidak, kita akan ketemu di forum. Ya. Oke. Baik.
Maaf, Pak. Berarti habis ini ada forum ya, Pak?
Ya, saya sediakan forum.
Oke.
Kalian kan belum melihat semua videonya, atau kalian sudah melihat, tetapi belum berkomentar, belum membuat pertanyaan-pertanyaan. Nah, saya kan tidak tahu kalian itu mengerti atau bingung atau mempunyai masalah. Nah, karena kesempatan di Zoom ini terbatas dan yang tanya itu biasanya cuma Edgar, Sultan, ya, dan beberapa teman yang lain, tidak banyak, maka saya coba gunakan media forum karena dari pengalaman sebelumnya, kalau di forum itu kalian lebih aktif, lebih banyak pertanyaan, gitu ya. Dan mumpung hari ini saya juga agak longgar, meskipun tidak harus selalu berada di depan laptop, di Zoom, tetapi saya bisa lihat, cek, ada pertanyaan masuk enggak di forum, untuk bisa saya jawab. Gitu.
Baik, Pak. Terima kasih.
Ya, jika tidak ada pertanyaan, oke, sampai ketemu di forum ya. Dan tolong lihat videonya, coba kerjakan soal-soal yang ada di bukunya. Kalau pakai bukunya Dutchman ya silakan, pakai bukunya Sigle ya silakan. Nanti akan saya posting juga buku dari Gurmi Gupta di Classroom. Silakan saudara gunakan untuk berlatih itu. Ya, sampai ketemu. Assalamualaikum.